Graphs of polynomial functions. To sketch or trace the graph of a polynomial function, we need to study first the following, starting with the leading coefficient test. So obviously, it has something to do with the leading coefficient or term of the polynomial function. Now, the leading coefficient test uses the leading term of the polynomial function to determine the right and the left-hand behaviors of the graph. Another thing to consider when we trace the graph of such function is the turning point. It is a point where the function changes from decreasing to increasing or from increasing to decreasing values. Now, if you recall about the quadratic function, particularly its graph, okay, we have a turning point on that graph, and that is what we call the vertex, the maximum or the minimum point of such graph. So in the polynomial function, we also have turning point, actually turning points. The number of turning points, unlike in quadratic function, there are more than one or two turning points. And how do we determine the number of such turning points? Okay, later on we will be discussing that. So let us proceed to the next slide. Now, what are the different steps in sketching the graph of polynomial functions or the graphs of polynomial functions? Particularly, we want to graph this polynomial function, y equals to x cubed minus 7x squared minus 7x plus 12. For the first step, we need to determine the end behavior. Meaning, we need to find out the behavior of the left and the right side of the graph of this given polynomial function. Therefore, we observe particularly the leading term of this function, particularly that is 2x cubed. Okay. So that is based on the degree and the leading coefficient. Basically, the leading term. So you will notice that the degree is 3, so we know that 3 is an odd number. So we have an odd degree. And at the same time, the coefficient or the leading coefficient, which is positive 2, is obviously positive. So if we have these two conditions, odd degree and positive leading coefficient, we have the behavior of the graph. And that is, of course, we have the leading term. So the end behavior of the graph is this. The graph falls to the left and rises to the right. Okay. So in this particular function, we have a graph whose left side is falling and whose right side is rising. Okay. Now, what if we have a polynomial whose degree is odd, but what if the leading coefficient is negative? Suppose the leading coefficient is negative. What would be the behavior of the end of the graph? Say the leading coefficient, again, negative, particularly negative 2x cubed. So what is the end behavior? Now, the end behavior would be like this. The graph rises to the left and falls to the right. Obviously, it's the other way around compared to this condition right here. Okay? But in this case, we have this function, so we have this end behavior, the first one. Okay? Next. What if, Okay, let us discuss all the possibilities. What if it is so happen that the polynomial function has an even degree? Say the degree is not 3 but other value of the exponent, and the leading coefficient is positive. Say the leading term is 2x squared. So what would be the end behavior of the graph? So the graph rises both to the left and to the right. Okay. And let us have the last possibility for the negative leading coefficient having a degree of even. So the end behavior is the other way around. Okay. Ayan. Particularly, we have a negative leading coefficient. So again, the end behavior, the graph falls both to the left and to the right. Now again, we have a particular given polynomial function. So the end behavior is what? The graph falls to the left and rises to the right. Since the two conditions are, we have an odd degree and positive leading coefficient. Now, what else do we need to consider other than end behavior of the graph? We need to determine its x and y intercepts. Okay? So first, let us consider the x-intercepts or zeros of this given function. So we need to factor this polynomial part, and upon factoring, each factor is equated to 0. But first, before we could do that, we need to set y equals 0 after factoring. So using using the synthetic division to factor this, we obtain this factored form. So that is quantity 2x plus 3 times quantity x minus 1 times quantity x minus 4. And from this factored form of polynomial equation or function, we set the value of y equal to 0. And from here, each factor equate to 0 and solve for x from each resulting linear equation in one variable. So in this particular factor equated to 0, we will find out that the value of x is negative 3 halves. And for the second factor equated to 0, we have x is equal to 1. And for the third and final factor equal to 0, solving for x, we have x equals 4. So these three values are the zeros or the x-intercepts. Now, for the presence of any zero multiplicity, we need also to consider that. But here, we don't have any zero multiplicity here. So we don't have any concern about this one. But what if there is a zero multiplicity? What will happen to the graph? Now, suppose we have an odd multiplicity, meaning the one x-intercept or 0 will occur 3, 5, 7 times. Okay? So, which means odd multiplicity. The behavior of the graph would be like this. The graph crosses the x-axis. And for those zero multiplicity that are even, the graph touches the x-axis and turns around. Now, since we don't have any multiplicity from these three uh, x-intercepts, we don't have, this is not our concern at this point. in this particular example. So with that, let us now proceed to the next thing we need to determine also, which is the y-intercept. Okay. Now for the y-intercept, we need to set x from this expression equal to 0, so that the resulting equation or expression on the right side will result to 0 from each of the first three terms. And obviously, your y is equal to 12, which is your y-intercept. Next, after determining the intercepts, we need to find the turning points or the number of turning points. Now, these are the peaks, the local maxima or the maximum point or points, and value or the local minima or the minimum point or minimum points of the graph. Now, the number of turning points is 1 less than the degree of the given polynomial function. So if we have a degree of 3 for this polynomial function, it means that the number of turning points of the graph is 3 minus 1, which is equal to 2. Now, to get the exact turning points, actually it requires the use of higher mathematics such as calculus. Now here, in tracing the graph, we could estimate the turning points of this graph. Okay. We could have a rough estimation of the particular positions of uh, those turning points. Now, okay, so two turning points. And at this point, the last step is to trace the graph or sketch the graph. So we prepare the graphing paper and the two coordinate axes and y. And we have the point of origin, and then we label some x and y coordinates in the Cartesian plane. And then let us start. So we begin with those obtained intercepts, starting with the x-intercepts. And these are negative 3 halves, 1 and 2. 4, I mean. For negative 3 halves, this is actually equivalent to negative 1.5. Now, along the x-axis, the coordinate negative 3 halves is between negative 1 and negative 2, somewhere along here. So let us plot the point on that particular location, which is this one, the blue dot. Along the x-axis corresponds to the coordinate negative 3 halves, which is one of the x-intercepts. And for 1, obviously that is at the middle or between 0 and 2. So this is where the point is located. And for 4, obviously, you plot the point here. Next, we have the y-intercept, which is equal to 12. So locate the coordinate 12 along the y-axis. And this is where we are going to plot the point. Then using smooth curves, we're going to connect these 4 plotted points. Now again, going back to the end behavior, that is determined by the odd degree and the positive leading coefficient. Let us recall the graph falls to the left. It means starting from this point, we draw a curve going this direction, going down. And for the right end of the graph, starting at this coordinate, we draw a smooth curve going up like this. Okay? So, Yun. But first, we could also trace first the portion of this graph. So let us have 2 connecting the y-intercept 12. Then we do the turning point of the graph and then connecting to 1 coordinate of the x-axis, and then we go down and then connect 4. So again, for the end behavior, we are now going to trace the left and the right end of this graph. So for the left side, according to the end behavior, it falls to the left. The graph falls to the left, and on the right side, the graph rises to the right. And there you have it. So this is the graph of this polynomial function. Okay? Next. Let us consider the second polynomial function. What if we have this equation, y equals negative x to the fifth plus 3x to the fourth plus x cubed minus 7x squared plus 4. So we also need to sketch the graph of this second polynomial function. So what are the things we need to determine first? First is, again, we need to find the end behavior or determine the end behavior of the graph. What will be the direction of the left side, the left end, and the right end of the graph of this polynomial function? Let us investigate. So we need to observe the leading term, and we know that the leading term is negative x to the fifth, having a degree of 5, and 5 is an odd. And the leading coefficient is obviously negative 1, so it's positive, less than 0. So if we have these two conditions, the end behavior of the graph would be this one. The graph rises to the left and falls to the right. So it's the other way around compared to the first example. Next, the x-intercept and y-intercepts or y-intercept. So how do we determine the intercepts of this polynomial function? Particularly finding the zeros or the x-intercepts first, we make use of the synthetic division. So let us proceed immediately to this step. So from the given polynomial part, we consider all the coefficients and the constant term. But you will notice that there is one particular missing term. Since after negative 7x squared, the next term is constant. Okay? One term is being skipped, and that is the term with the degree of 1. So we need to insert 0 for that particular missing term in the synthetic division. So taking those coefficients, we have the first one taken from the first term, negative 1, followed by plus 3 taken from the next term, 3x to the fourth, then followed by 1, minus 7. Then, before we consider the constant term, we need to insert plus 0, and then followed by plus 4. Then, consider one possible root, which is one of the factors of 4. So we will begin with the smallest factor, and that is negative 1. And then we carry out the synthetic division process. So we bring down negative 1 times negative 1, so that is plus 1 added under plus 3. So that is plus 4 times negative 1 is negative 4 to be added to positive 1. So that is negative 3. Negative 3 times negative 1, that is plus 3 added by negative 7. So that is negative 4. Negative 4 times negative 1 is positive 4. added by 0. So that is positive 4 times negative 1 is negative 4, and then 0. And since the remainder is 0, meaning we got the right root. Or actually, this is already the 0 or the first x-intercept. Meaning there is no need for us to uh, factor this polynomial part. Because this one right here is one of the x-intercepts we're looking for. So let's just keep on going with the synthetic division process. This time, we consider this next row of numbers, excluding 0, because this is a remainder. So, okay, we check that. So, we copy these 5 numbers, negative 1 plus 4, negative 3 minus 4 plus 4. And then we use another root. We could use again negative 1, but because there is also a possibility of 0 multiplicity. Okay. Now, if in case we repeat using negative 1 in the synthetic division and the resulting remainder is not 0, it means we only have negative 1 x-intercept. And we go to the next factor of 4. But here, let us try negative 1. So bring down negative 1. Negative 1 times negative 1 is positive 1 added to positive 4 is positive 5 times negative 1 is negative 5 added by negative 3 is negative 8. Negative 8 times negative 1 is positive 8 plus negative 4 is positive 4 times negative 1, negative 4, and this is 0. So it means negative 1 occur twice. So we have the second x-intercept, which is also negative 1. Then let us go on with the synthetic division. This time, we consider this next row of numbers, negative 1, positive 5, negative 8, positive 4. Then, we consider another value as the next factor of 4, particularly positive 1. Then we do the same process of synthetic division. We bring down negative 1 times 1 is negative 1, plus 5 plus 4 times 1 is plus 4, added to negative 8 is negative 4, negative 4 times 1, negative 4, and this is 0. Again, we found the next x-intercept or 0. This time it's 1 or positive 1. Then we go on with the process. This time we consider negative 1, positive 4, negative 4. Then for the next possible root, most probably that is 2. Then let's proceed. Negative 1, bring down negative 1 times 2, negative 2. Plus 4 is positive 2 times 2, positive 4, 0. So we have the fourth x-intercept, which is positive 2. And the last value for our x-intercept is to be taken from this row of 2 numbers. And this is actually negative 1 plus 2 is negative x plus 2, equated to 0. And from this resulting equation, we solve for x. And that is equal to 2. Another check. So here we have 5 zeros or x-intercepts. And some of these 5 values, 2 are repeated. Okay? And these 2 zeros are negative 1, which is occurred twice or times 2, as well as 2, which also occurred twice also. Okay, which also occurred twice, together with 1. So, we have two multiplicities, negative 1, which is times 2, and positive 2, which is times 2. And their, their multiplicity are both even, since 2 is an even number. So what does this mean when it comes to the behavior of the graph? Yeah. Now, for those x-intercepts or zeros that occur twice or times 2, it means that the graph touches the x-axis and turns around. So, with that, let us now go to the y-intercept. Basically, we need to set the value of x from this polynomial to 0. And then, simplify the resulting expression on the right side. So, with that, we found out that the value of y, or the y-intercept, is equal to 4. Okay. And then, finally, we have to determine the number of turning points. Since the degree is 5, therefore the number of turning points is 4. Because the number of turning points of the graph of polynomial is 1 less than the degree. Okay. And with those things, we can now go to the sketching of the graph. Okay, I have already prepared the Cartesian plane with some labeled coordinates along the x and y axis. So let us plot those intercepts. Okay, so we have negative 1, this one, positive 2, and positive 1. And along the y-axis, whose intercept is 4, so we plot the point here. Since along y-axis, the coordinate is 4. And then, let us now use smooth curves to trace the graph. Let us start with the end behavior. Now for the end behavior, we have the graph rises to the left and falls to the right. So if this is where we start sketching the graph, from this point, we draw going up, no? Yeah. And on the other end, from this point, we go down. Tama ba? Okay, falls to the right. So, this is how we trace the graph. And then, going back to those zeros that are multiplicity or that occur twice. So, if this is your negative 1, it means the graph will just touch the x-axis and turns around. So, same thing with this one. 2 is a multiplicity. So, the graph will just touch the x-axis, meaning it will not cross like this, in this way. So, it will turn around after touching the x-axis. It goes this way. And then, going up, crossing this point. Yun. Yun. Then, from this point, we go up using a smooth curve and going to this point. Turn around, okay, turning around, and this one. Yan. Okay. So, to verify the accuracy of the graph, let us count the number of turning points. According to this, the number of turning points is 1 less than the degree. So, we have a degree of 5, so minus 1, that is equal to 4. And from the graph, is it really 4 turning points? Let us count. 1, 2, 3, 4. So, tama tayo. Then, for the multiplicity, for those x-intercepts that occur twice, we have 1 or negative 1 and positive 2. So let us verify. Now for those x-intercept that occur twice, since the multiplicity is even, so the graph touches the x-axis and turns around. So the graph touches the x-axis at -1 and turns around. In the same manner, the graph touches the x-axis at coordinate 2 and turns around. Okay. It means we have just accurately drawn the graph of this polynomial function in number 2. Now to continue, let us proceed to the next slide. Now for our third polynomial function, say y is equal to x to the fourth minus 7x squared plus 4, or 4x rather. Again, y equals x to the fourth minus 7x squared plus 4x. Now, to trace the graph of this third polynomial function, of course, we can factor the right side and determine the x-intercepts. And these are -3, 1, 2, and 0, which is taken from the factor x, which is equated to 0. Then for the y-intercept, set x to 0, and we found out that y-intercept is 0. And then for the degree and the leading coefficient, to determine the end behavior, so we have uneven degree with positive leading coefficient, which means the end behavior of the graph is what? The graph rises both to the left and to the right. And this is the graph. Now for the number of turning points, it is 1 less than the degree. Since the degree is 4, meaning the turning points are 3. There are 3 turning points, so let us count. 1, 2, 3. Okay. Next. Fourth, probably our last polynomial function. Okay, the factored form of the polynomial part. So from each factor equated to 0, the x-intercepts are -3, -1, +2, and 4. For the y-intercept, set set x to 0 and solve for the resulting expression on this side. And you will notice that the y-intercept is -4. Now for the end behavior of the graph, we have an even degree, particularly 4, and the leading coefficient is negative. So the graph falls both to the left and to the right. And what would be the appearance of the graph of this polynomial function? So if the degree is 4, the number of turning points is 3. So we have 1, 2, and 3. And this is your graph.